Today we are going to cover section 6.4, logarithmic functions. So write down your essential question: how do you use logarithms to model a variety of situations? Copy example number 1 and we'll start once you are ready. Pause. So evaluate without using a calculator. We need to be able to find the value of x. So 2 to what exponent is equal to 8? 2 to the, or 2 to the what power is equal to 8 will be 3. So therefore x equals to 3. Do you agree? 2 to what exponent is equal to 16? 2 to the fourth power. So x is equal to 4 because 2 times 2 times 2 is 8 times 2 will be 16. 2 to what exponent is 12? Well, 2 to the third power is 8. 2 to the fourth power is 16. So therefore, it should be somewhere between 3 and 4, 3.5. That's a good estimate. So therefore, logs are used to be able to find exponents that are decimal. And we can actually use a calculator to be able to calculate the logs. But we'll come back to that on the next lesson, on lesson 6.3. So take the time to copy or paste your cutout, and we'll start once you're ready, and go and copy example number 2. Definition of a logarithmic function with a base of a. Where x is greater than 0, we want it to be positive. A is greater than 0, we want it to be positive, and we don't want the a to be 1. So therefore, this expression y equals log base a of x, where a is your base, so we read it as log base a of x, if and only if x equals a to the power of y. So therefore, we can rewrite those two expressions. They're equivalent. One is the same as the other. The function given as f of x, that is a log function with base a. It's called a logarithmic function with base a. So let's go and evaluate without using a calculator. We know that we can rewrite logs as exponential function. And the way that we want to think about it is, what is log base 4 16? Do you remember from last year? You want to think about 4 to what exponent is 16? So this is the base, the 16 stays here, the 4 to what exponent is 16? 4 to the second, therefore that will be equal to 2. Got it? Equals. Sometimes they'll place an x in here. I prefer to just think of it more logically. I prefer to be able to say 3 to what exponent is 27? 3 to the third power. 5 to what exponent is 25? 5 to the, so 5 to what exponent is 25? 5 to the second power. Correct. So therefore, log base 5 of 25 is equal to 2. Now your calculators do have that built in. So let's see if we can find it. Sometimes I have, on the TI-84, it's something new that they added. So therefore I'm going to go into alpha, y. And I'm going to move to the right and see if I can find it here. You see it, number 5? If you have an older TI-84, then you're not able to do this. It's something new that they have added to the calculators, but that wasn't there before. So 5/25 gives you 2. So therefore, D, E, and F. Go and copy them down. See if you remember. That one should be an easy one. E and F. Go and pause it. So let's see. 9 to what exponent is 3? 9 to the second power. Now, if there's no base for this log, do you remember what the base is? Yeah, if there's no base, we say is a base 10. That is what we call a common log. And if you notice on your calculator, we have a log. It doesn't show anything underneath. Automatically is base 10. If you notice, there's a little 10 underneath the log. So therefore, 10 to what exponent is 100? 10 to the second power. So if I type in 100, that is correct. How about letter F? 5 to what exponent is 1/25 without using a calculator. So 5 to what exponent is 1/25. So let's think about if it was, remember, logs are basically exponent. So 5, or let me rewrite the opposite way. 1/25 is equal to 5 to what exponent? What is the exponent? Correct, -2. If it was just 25, then it'll be, if it was just 25, it'll be to the second power, right? But because that's 1/25 will be -2. Let's continue to some of the properties, and then copy example number 3, and we'll start once you're ready. Go and paste it, copy it, and we'll start. Pause it. So some of the properties of logs. We'll continue with 6.3 next time, when we talk about some of the other properties. But I prefer to cover section 6.4 first. So log base a of 1, it's always equal to 0, because a to the 0 power, any number to the 0 power is equal to 1. So therefore, every time you have a 1 in here, it will be equal to 0. The log of any base of 1 gives you 0. Why? Because any number to the 0 power gives you 1. This tells you a to the first power is equal to a, which makes sense, right? In this case, we can think about the log base a and the a cancels, it gives you an x, and vice versa. The base and the log cancels because they're the inverse of each other. And we'll talk more about that once we graph them. And the last property tells me that if they have the same log with the same base, then the x and the y should be equal to each other. And we'll do that once we solve an equation. So let's go through example number 3. And and that one is called a one-to-one property. So let's see. You can remember the formula that every time there's a 1 should be equal to 0, correct? 5, or you can go 5 to what exponent is equal to 1, 5 to the 0 power. 3 to what exponent is equal to 3? 1. So 3 to what exponent is equal to 3 will be 1. Or we can think of being the inverse property, just like we have here. We can think about the log base 3 and the base cancel, and you're left over with the exponent of 1. But we'll go over that a bit more once we start solving on 6.5 equations. We can think about the base and the log cancels each other out, so therefore this is equal to 30. If they have the same base, then they can cancel each other out due to the inverse property. So try D, E, and F. Go and pause it, see what you get, and then we can continue once you're ready. You got it? So 3 to what exponent gives you 1? Yeah, every time you have a log of any base of 1, it has to be 0. 3 to what exponent gives you negative 9? Let's see. Negative 9 is equal to 3. What is the exponent here? Is it negative 2? No, because if it's negative 2, we know that 3 to the negative 2 is 1 over 9. It's not negative 9. So not possible. Do you agree? Let's try the next one. 5 to what exponent gives you 0? So 5 to what exponent? Well, actually, let's write down the other way. 0 is equal to 5. What is the exponent? Once again, not possible, correct? Because if it's 5 to the first power is 5. 5 to the 0 power is 1. 5 to the negative 1 is 1/5. It can never be 0. So therefore that is not possible as well. So let's go through example number 4. Graph each function in the same coordinate plane. And actually, I'm going to use 2 different ones. So we can just say graph each function. I prefer to use 2 different graphs for this problem. Let's make 5 by 5s. Two, 4, 5, 2, 4, 5. And you did this before last year as well. So a lot of the stuff that we're going to cover is review by just a little more depth, a little faster pace. So we got this one in 6.2, correct? So we know that this is a exponential growth or decay. This is an exponential growth. We're just going to plug in values for x. We'll give it back values for y. We're just going to plug in a few points. Plug in is 0. 2 to the 0 power is 1. 0, 1. And we talked about that being the y-intercept. We have plug in a 1. 2 to the first power is 2. 1, 2. Plug in a 2. 2 to the third power is 2 to the second power is 4. Plug in a 3. Gives you 8. 2, 3, 2, 4, 6, 8. And now we also know that we have a y-intercept, and we can plug in a negative 1, gives us negative 1/2. Plug in a negative 2, gives you negative 1/4, and so on. So therefore, we know the graph comes from here, very close to the x-axis, and then it collects all those points, and it goes up very fast as well. Where we know that y equal to 0 for the asymptote, we know that our domain in our range, we know that our domain, it's all real numbers from negative infinity to positive infinity, and that your range is from 0 all the way to positive infinity. Now let's graph the log. I'm going to make a quick table of values. Once again, I'm going to plug in a few points, not too many. I'm going to plug in values for x, will give me back values for y. And we want to be able to think about some of the properties that we cover. So can we plug in a 0? So if I plug in a 0, will give me log base 2 of 0 is equal to the number. 2 to what exponent gives me 0? Correct. We decided that that's not possible. So therefore, we don't want to plug in a 0 because that's not possible. So therefore, we're going to plug in a, what's after 0? A 1. Let's go and plug in a 1. And we have the log base 2 of 1. 2 to what exponent gives me 1? 2 to the 0 power. So my first point will be 1, 0, 1, and then stay there. Now, I'm going to plug in a 2. Log base 2 of 2. 2 to what exponent gives me 2? 1. So plugging in a 2 gives me 1. Plugging in a 2 gives me 1. What should be the next number that I need to plug in? Remember, it should be 2 to what exponent gives me 4, correct. Log base 2 of 4 will give me 2 to what exponent gives me 4? 2 to the second. So your next one will be 4, comma 2. 1, 2, 3, 4, 1, 2. If I want to plug in another number, what should it be? It should be a 8. If I want to start with getting whole numbers, then it'll be log base 2 of 8 will give you 3. But there's not enough space. And the next one will be 16, correct. So therefore, or asymptote, because 0 will be undefined, and if we want to be able to go somewhere in between, what should I plug in a number in between? I can do a 1/2, correct? Because the log base 2 of 1/2, what will that be? 2 to what exponent gives you 1/2 will be -1. And then if I plug in a 1/4, will give you -2. So therefore my graph path will never, we cannot plug in a 0 because at 0 will be not possible, will be undefined. So therefore the asymptote now is going to be a vertical asymptote. So therefore the equation will be x equal to 0. It crosses the x-axis at 0. And now your domain and range. For your domain will be, the first value you can is from 0 all the way to positive infinity, but we cannot plug in a 0. So therefore, it will be parentheses, and infinity always gets parentheses. Range will be all real numbers, from negative infinity to positive infinity. So what happens is that your exponential function is the inverse of the log. And that's why you start to see the word inverse property. So therefore, if you have your graph, which you should, somewhere in your notes, section 6.1, if I have my graph and I sketch it, and I even place this point here, and that point there, and I take the inverse, basically your x's and y switch, right? Your x's becomes your y, and your y becomes your x. Then that is, voila. Isn't that impressive? Your log your exponential function is the inverse of your log. Boom. So what does that mean? So remember what it means. It means that if you plug in a 2 here, you end up with a 4. So therefore, if you plug in a 4 over here, you end up with a 2. So they undo each other. And that's going to help us as we solve section 6.5. Since they undo, it's set in addition and subtraction. So if it's adding, you subtract on both sides. Multiplication and division. If it's multiplying, you divide on both sides. So now we're going to use, because the inverses of each other, we can use that to solve equations. But now let's go to the formal definition for some of the graphing now that we develop the concept of graphing. Go ahead and paste your code, copy example number 5, and we'll start once you are ready. Go and pause it. So logarithmic function f with base a in standard form is denoted by the following function. Notice that we still have an h and a k. So this one shifted left or right. This will shift it up or down. And notice that in this case, the logs are the same equation. You don't see the negative that you did with exponential. But the biggest difference is going to be the value of a. If it's greater than 1, it's going to be just like we graph on the example number 4. But if it's less than 1, it's basically going to get reflected on your x-axis. If it's between 0 and 1, remember, we don't want a to be 0 and we don't want a to be 1 either. So here are basic characteristics. The domain, notice that before on section 6.2, we had that took me a while. Let's see. For the last exponential growth, your domain, and now it's your range. Now for this one is to be your range, and now is your domain. Notice that your y-intercept, now that is your x-intercept. Your vertical asymptote now is going to be x equal to h. It's a continuous function and it's 1 to 1. Do you remember what does it mean to be 1 to 1? That means that if you take the inverse is also a function. And of course, that's an exponential function. So both of them are 1 to 1 because exponential is the inverse of a log and the log is the inverse of an exponential. Now let's go through a graph example number 5, and the process will be very similar to what we did on section 6.2. Let's go and build a 5x5 graph. And now we are, once again, well, let me do this one as well since we have it here. So once again, we're going to go through the process of graphing only the basic part of the graph. We're not going to graph the entire graph. We're just going to shift it afterwards. There's some books that actually will just graph the entire graph, but then we start losing some of the concepts of the intercepts, the shifting, your asymptotes. So I prefer to graph it just the basic part. Makes it a little bit easier to understand. Otherwise, we just plug in the numbers into the calculator, plot in, and that's it. So let's go graph. We're going to graph f of x is equal to the log base 3 of x. And I'm going to make a table of values. I need to decide what values to plug in for x, and I just need to plug in 2 values, should be sufficient. Remember that this is a log, the base is 3. So it used to be an exponential, now it's going to get reflected. So now it's going to be a log. It's going to look something like this. You want to get used to the shape. And every time I see the log, I always think of the vertical asymptote. So that should be able to help you remember the shape, right? The L, you see it? So therefore, plug in values for x gives you back values for y. What value should I plug in for x? Can I plug in 0? No. Can I plug in 1? Yes. So I'm going to plug in 1. Log base 3 of 1. That'll be 0. So 1, 0. Remember, that will be always your first point, your x-intercept. Where before we could calculate your y-intercept right away with exponential functions. Right? Now that is your x-intercept. Now what is the next value that I should plug in? Correct, it's 3. Because log base 3 of 3 gives you 1. 3, 1. Now before I shift it, my asymptote will be on the y-axis. So it should look something like this. Getting closer and closer to the asymptote, but never crossing it. A little closer. And now I'm going to shift it. This will shift my graph to the left. Each point will be shifted to the left 2, 1, 2, and down 1. This one to the left 2, and down 1. My asymptote got shifted to the left 2 and down 1. So therefore, your asymptote will now be your h, x equal to negative 2. Where before, your asymptote was your k, because it was horizontal, y, h, k, y, k. Now, this is your h, that'll be your asymptote, because it got shifted to the left too. And therefore, now I can just connect them. Remember, I placed 2 and still I overlapped it, so I should place this extra circle. Kind of helps me out. So it comes from here, and then it's going to collect that point, and then this point, and then it's going to continue rising. So there's no horizontal asymptote. It's going to just continue slowly rising up, and it's always going to be rising up slower, but it will still be rising. So therefore, the next thing I need to find is my domain and my range. Where my domain will be starting at negative 2 all the way to positive infinity. And my range are all real numbers. Correct? So let's try the next one. On the next one, let's see, the base is 1/2. So therefore, what used to be an exponential decay, once you take the inverse, is going to be like this. So you want to get used to the shape. I see the log, so I think of the L. So therefore, I'll graph the basic part of the graph. So there'll be f of x equals the log base 1/2 of x. I'm going to plug in values for x, will give me back values for y. And you can decide what values to plug in, but which one will be the easiest value to plug in? Can I plug in a 0? No, you can't take the log of a 0. 1. Log of 1/2 base 1. No, log base 1/2 of 1 gives you 0. That will always be your first point. What is the next number that I should plug in? A 1/2. Log base 1/2. Log base 1/2 of 1/2 gives you 1. So 1/2 gives you 1. And that's how we get that shape. So if I was going to graph, now you can plug in more values. You can actually plug in a 4 if you want, or plug in a 2. If you plug in a 2, what will it give you if you plug in a 2? That is a good question. Think about it. What is log base 1/2 of 2? log base 1/2 of 2. 1/2 to what exponent gives you 2? 1/2 to what exponent gives you 2? -1, correct? Because basically you just have to take the reciprocal, so it gives you 2. So if you plug in 2, it gives you -1/2. So plug in 2 gives you -1. And we can continue plugging numbers, but we just need 2. I can plug in a 4, gives me -2, plug in an 8, gives you -3, and so forth. But now, my graph without shifting it will be something like this. Oh, messed up. That wasn't part of order. But now I just need to shift it up one. So everything gets shifted up one. This one gets shifted over here. That one gets shifted here. And we're going to ignore this one. How about our asymptote? Our asymptote used to be here. It got shifted up one. So it stays in the same place. Since there's no h, our asymptote is x equal to 0. And now I'm going to graph it. You can erase your previous graph. I do need to see the previous dots to make sure that you actually shifted it. So just slightly erase it. And now I can find my domain and range. My domain. So find the positive, see what you get for your domain and range. Correct. Domain is from 0 all the way to positive infinity. Range is all real numbers. Example number 6. Go and paste it, copy it down, and we'll start once you are ready. Pause it. So the natural logarithmic function, the function defined by f of x equal to log base e of x, can be written as follows: ln of x. So something that you want to be able to keep in mind, that every time you see ln of x is the same as the log base e of x. But we use this so much that it got its own abbreviation. So when we graph, it's going to be exactly the same process. Remember, e is 2.7. So let's go and graph 6, and then I'll let you guys graph b by yourselves. So we'll graph a together. So once again, we are going to graph just the basic part. We're not going to include the 3. The 3 is that going to be, that's going to be just shifting it up 3, correct? So let's go see f of x equals ln of x. I'm going to make a table of values, and we need to be able to decide what values should I plug in for x. What should be the first value that I should plug in for x? Now remember, this is the same as f of x equals the log base e of x. Same thing. I should plug in a, can I plug in a 0? No, you can't take the log of a 0. And even if you try it in your calculator, the log of 0 is, oh, so Diaz, you forgot the parentheses. Fine, there's a parenthesis. Yeah, same thing. You cannot take the log of a 0. You cannot take the log of a negative number either. So -2. And we know that because if we actually look at the basic graph, which we did here, there are no values to the left, correct? All the values start after 0, you start getting values for the graph. So now, cannot plug in a 0. What value should I plug in for x? Correct, a 1. Plug in a 1, log base e of 1 gives you 0. What should be the next value that I need to plug in? That is the question. Should plug in e, right? And e is 2.7. Log base e of e gives you 1. So 2.7 gives you 1. And those are the only points. If I need to plug in another point, let's assume that I need to get another point. What value should I plug in next? E squared. If I plug in an e squared, will give you 2. And at that point, we can calculate 2.7 times 2.7, but we don't need it for purposes. I know that my horizontal, my vertical asymptote, right? It's going to be here. And now we just need to shift it up 3. So if I was going to graph it here with my pencil, very lightly, that'll be the graph. So see how I can go to the right. You have to get closer and closer and closer and closer and closer and closer and closer to your asymptote. And now I just need to shift it up 3. Each point, 1, 2, 3, 1, 2, 3. And now my asymptote was here, got shifted up 3, stays in the same place. And now we can graph. Closer and closer and closer, but never crossing it, never touching it. So several things that we need to finish up. X equal to 0. My domain and my range. My domain will be from 0 all the way to positive infinity. My range will be all real numbers. So try letter B. But before we actually start, let's talk about and see what should be the shape. I know for this one is log base e, so therefore it should be like this, right? And we actually had it here. How about for this one? What happens when you have a negative? Remember, if it is supposed to be like this, but now it's going to get reflected. So therefore, now it's going to come from the top all the way to this, something like this. With your vertical asymptote, think of the L here for the ln. That helps you remember that you should have a vertical asymptote. So graph it, see what you get, and then we can compare our answers. Go and pause it if you need more time. Excellent. So in this case, we are graphing the basic part, so f of x. We're not leaving the L negative behind. This will be the basic part, or basic graph. And then we're going to have to shift it to the right too. I'm going to make a quick table of values. I'm going to plug in values for x, which will give me back values for y. What is the first number that I should plug in? I should plug in a 1. Gives you ln. Remember that this is the same as f of x equal to negative log base e of x. Use something that you need to remember. E to what exponent gives you 1? E to the 0 power. Anything to the 0 power gives you 1. So that will be always your first point. And now the negative 0 times negative is 0. Plug in a e. E to what exponent gives you e? 1, but it's actually negative 1, right? Let's not forget about the negative. So 2.7 and down 1. So therefore, my asymptote is now here. And let me just make a quick sketch so I don't forget what the shape should look like. You always want to be able to think about the shape before you start graphing it, because otherwise you're not too sure whether your points look correct. And if you make a mistake, then it kind of throws the whole thing off. And now I just need to shift it to the right 2. 1, 2, 1, 2. And my asymptote will be 1, 2. So therefore now my asymptote. Remember that your asymptote will be guided by your h. In this case it's x equal to 2 because your h value is 2. Last thing I need to do is my domain and my range. My domain will be starting from 2 all the way to positive infinity. My range, it's all real numbers. Example number 7. Now example number 7 looks challenging, but it's actually pretty easy. So take the time to copy it down, and we'll start once you are ready. Go and pause it. And take the time to read it. Go and paste your example number 7. Take the time to read it. And pause it, and we'll start once you read it, highlight a few things, see if you understand it. And you actually might be able to do it all by yourself. So let's read through it. Some populations initially have rapid growth, followed by a declining rate of growth, as illustrated by the graph below. So notice that the graph is increasing pretty fast, and then the growth slows. One model for describing this type of growth pattern is a logistic curve. So this is a logistic curve given by the following function, where y is the population size and x is the time. A and b are just going to be two numbers depending on the initial and other variables. An example is a bacterial culture that is initially allowed to grow under ideal conditions, and then under less favorable conditions that inhibit growth. The logistic growth curve is something that it's also called a sigmoidal curve. From sigmoid, not too sure. Let's go to example number 7. On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by the following equation, where t is the time and we want it to be greater or equal to 0, right? You can't go back in time. Where y is the total number of students infected after t days. So you have 5,000 students. Y is the number of students infected after t days, where t is in days. The college will cancel classes when 40% or more, 40% or more of the students are infected. How many students are infected after 5 days? Now, they give us the equation, so we are going to use, or we can use a graphing calculator, but let's use Desmos for this, since it's going to allow me to do a little faster, but the graphing calculator works fine as well. I'm just going to click on graphing calculator. Y equals, actually let me type in f of x. It makes it a little easier when we're trying to calculate values. Now 500 by 5,000, 1 plus 4999 e to the power of negative 0.8 t. And it's not t. If you use t here, then I need to use t over here. Now sometimes when you use some variables, Desmos does not like all the variables, but in this case t is good for them. So now we can adjust our window. Let's adjust window because they're asking for 5 days, and notice that 5 we don't see it yet. So let's go into the window, and our x, let's go and do from -5, what should be, to +10, and the y from -50 to, let's go high, 300. Let's see how that looks. We should be able to find 5, right? Otherwise we can do a little lower or higher. So you get to decide, you get to play around window where there's some decimals in your graphing calculator. So in this case, I left it to 200. That seems like a good. Now, we're actually going to do it all by using the graphing calculator. After 5 days, I can just plug in a 5. And I can use my calculator to do that as well. So if I want to use my graphing calculator, I can actually take the time to type into my graphing calculator, and I can type in 5,000, 1 plus 4999. And actually, let's go and write that down. So as part of your work, you do need to show me that you worked it out. And 54. So let's see if it matches here. In decimals, you just do F of 5, and that's perfect. So let's write that down. For part A, we have y equals to 5,000. Remember that you do need to show me how you got your answer, whether you just write down the substitution. So therefore, y is equal to 54. Do we need this symbol? No, in this case, we are talking about people, right? So students. So 54 students are infected. After 5 days. B. How many days will the college cancel classes? So y is how many students? And the college will cancel classes after 40%. So I need to be able to find out what's 50. So 5,000 multiplied by 40%, which is 0.4. Correct? So just use the calculator. 5,000 times 0.40 gives you 2,000. We want to be able to find out how long will it take for 2,000 students to get infected. So we can actually set up an equation. 2,000 equal to 5,000 over 1 plus 4999e negative 0.8 t. And we can solve for t, but we won't know how to solve it until we get to section 6.5. So for now, we're going to use decimals, and you remember how to solve it. So I have this part of the equation here, and then I'm going to type in another function. So just going to type y equal to 2,000, 1, 2, 3. So therefore, I need to adjust my window to, let's see, 2,000, let's do 3,000, right? So we can see it. And there's our graph. We shift to the right, and we can just click on the intersection. So how many days will it take? It will take 10 days. After 10 days, the college will cancel classes. And the last example for today. Take the time to paste it or copy it down, and we'll start once you are ready. Now, we've done linear regression before. We've done quadratic regression. We've done exponential regression on the last set of notes. See if you can work this out by yourselves. You can use decimals or you can use a graphing calculator. For my purposes, I'm going to use a graphing calculator, so I can, or you can, but you can use decimals as well. I'll go and pause it, work it out, and then we can check our answers. So the table, let's go over it then. At this point, you should have worked it out. The table lists the number of monthly active Twitter user accounts in millions for 2010 to 2017. And here's the code. You can actually look aloud the statistics on this website. Using the graphing utility to make a scatter diagram of the data where x is equal to 1 for 2010. So there's 4. Let me label those because they usually start at 0, right? So this gets 1, 2, 3, 4, 5, 6, 7, 8. I'm going to type those as my x values. Use least square regression. Now, whenever they use the word least square regression, it's basically just a regression. So that's another terminology. So once you go into stats, you'll hear more about that. To determine A and B, so the following function models the data. According to this model, what is the number of monthly active users accounts for 2020? So let me go through, and I'm going to use my graphing calculator for our purposes today. I'm going to go under stat. I'm going to go into edit. If you have any data from there, just go and clear, enter. It'll clear the data for you. Clear, enter. So we have 1, 2, 3, 4. 30, 68, 138, 204, 255, 302, 310, and 328. Oh, 328. So that looks good. Perfect. So now I'm going to go under graph. Oh, a graph in there. So this calculator doesn't allow you to stop it. It has to finish all 3 graphs that we had before from section 6.3. Why? I'm going to clear up all my graphs. And I don't see anything. So what I need to do, I need to be able to do my window. Now you can also go under zoom and see if it does the fit. No. Why? Plot selected, so it's fine. Let me go under window, and let's say it's going to go, let's say, from negative 2 to what's the maximum value? 8, so let's go up to 10. Y value smallest is 0, so let's go from 0. Oh, scale is 1. Y should be from 0 all the way up to 350. Let's go and graph. And now we can see it, right? And now you can see that we're going to use a log regression. So therefore, I'm going to go under stats. I'm going to calculate. LN regression is here. Now I want to make sure I save my graph. So I'm going to go under vars function, press number 1 to select the first equation, and then I'll calculate. Notice that gives you the same model. So I'm just going to write it down. A. Oh, it's actually. Well, let's go over here, this first question graph. Notice that this will not be a linear function, right? And it's also not a quadratic, so more of a log. So a log regression. And notice that we actually have a natural log only. B. Let's go and write it down. F of x is equal to, what were the values? They're always in here. Just have to negative 6.53 plus 159.11. ln of x. And see, according to this model, what is the number of monthly active users accounts for 2020? So let's see, according to the model, I can go into, let's go and graph it first. And I'm going to go under calculate. I'm going to calculate the value. And I'm going to press 2020 should be one number. Let's see, it won't be 20. So 9 will be 2018. 10 will be 2019. 11 is 2020. So I'm going to plug in 11. 2011, oh, not found. So what happens is that it's actually looking for the data. So quit, let's fix that. Why? I don't want to plot the data, I just want the function. I want to click on the data. So now it's only the function itself. So whenever I actually type in a calculate value, I'll type in 11 again. Interesting. Let me try again. Calculate. I'll figure out why, but for now I'm just gonna cheat. Ignore this. Okay, so there's still the same graph. Let me go and calculate value 11. So back in 11, I should be able to get a value for x, right? We'll do 12. Maybe that's why. Be patient. So let's see, y, I'm gonna go calculate again, and I'm gonna do value, and that's 11. Oh, that's why. So therefore, according to 2020, there should be a 375 if we round it up. So according to this model, the number there will be 375 million active accounts, active users, right? So now let's go into statista.com and see if our projection is actually accurate. So Statista is a free website that will give you tons of statistics. The only thing that you do need to be able to have an account. You can just make a free account. And let me just go in here and just type in. We want Twitter. We have a monthly active. They usually say users instead of accounts, correct? And we actually want a world. We have Twitter number, month of active users. We actually want the total. So this might be it. So they have it from 2010. From the rest of 2010, they have 30. At 2012, they had 138, depending on the quarter that you look at, first quarter. So therefore, at 2020, we only have 2019. So 330. So notice that in this case, 375 seems a little high, correct? So even though it does give us a good projection overall, it's now accurate, but it does notice that in this case it does increase pretty quickly, and then it starts to go flat. So this will conclude the lesson for today. Have a great day, and I'll see you guys next time.